This video acts as a review of oxidation numbers. Some students may have learned oxidation numbers in a previous semester, while some may have not. This is due to a change in our curriculum where this was taught in General Chemistry 1 versus General Chemistry 2. Regardless, it is always good to review whether we've learned something already, so please still complete the review portion of the lecture guide whether you've learned about oxidation numbers or not. If you would like to read more on oxidation numbers, then you can look towards Chapter 9 of your textbook to read and review. So, we can quantitatively, so using numbers, determine what is being oxidized and reduced in any chemical reaction. Okay, we can use numbers to determine this. So we can physically see through the numbers how is the charge changing to determine how the electrons are moving around. And this is referred to as the oxidation number. The oxidation number is the charge of an atom, or charge that the atom would have if electrons were transferred completely. So oxidation number is kind of just a little fun like Sudoku type game I like to compare it to, because you're just kind of filling in numbers. But it's all whole numbers, there's no halves or anything like that, it's just counting. So we have the example here, which we already kind of have been looking at, honestly, since we've been doing ionic compounds. So we have H2 reacting with F2, creating HF. This is exactly how we started our previous problems. I said, okay, H2 is elemental, right? If it's elemental, it's coming right off a periodic table. It has a charge of 0. That charge can be referred to as the oxidation number. So H2 had a charge of 0. Its oxidation number is 0. Okay, so we've already kind of been doing oxidation numbers. F2 as well is elemental fluorine. Elemental fluorine comes right off the periodic table. It hasn't lost any electrons, gained any electrons, so it has a charge of 0, meaning its oxidation number is 0. Again, in our previous examples, I then said, well, let's look at our products. Okay, our product is an ionic compound. In this case, it's a strong or an acid, so it can separate into its two individual ions. So if we were to look at the charge of those, well, we know F has a charge of -1 from the periodic table, and H has a charge of +1 in order to balance out that fluorine. So again, it's just relating to our charges of what we've done when we've quantified ionic substances. Okay? So, in HF, the oxidation number of hydrogen is now +1, and the oxidation number of fluorine is now -1. We can then use that, in the same way we did in our previous examples, to determine what's being oxidized and what's being reduced. So, hydrogen went from 0 to +1. If we went from a charge of 0 to a +1 charge, we had to lose electrons. Right? If we become a cation, we lose electrons. That's our definition of cation. If I got a +1 charge, I lost electrons. I have more protons than I do electrons now. For fluorine, I went from 0 to -1. If I went to a more negative charge, I gained electrons. Okay, this is exactly what we did in our previous examples. So we already got a head start on oxidation numbers. If we gained electrons, that means this is reduction. And if we lost electrons, this is oxidation. Okay, so we'll practice this a little bit more. The oxidation number is sometimes referred to as the oxidation state. Okay, and these oxidation states have individual numbers for the specific elements, as well as an overall contribution to the molecule at hand, which we'll look at through our examples today. So we do have some guidelines for assigning oxidation numbers. So these are really good rules and guidelines to follow when determining oxidation numbers in compounds that are a little bit more complex than our basic ionic compounds, or if we wanted to find the individual oxidations of all elements, say like if we had an ionic compound with a polyatomic ion, where I have multiple elements that are both ionic or metals and nonmetals. So The first one is the one that we've been saying all along. The oxidation number of an element in its elemental form is 0. The charge of an element in its elemental form is 0. So that corresponds to its oxidation number. The oxidation number in any chemical species must sum to the overall charge of that species. So, if the molecule overall has a neutral charge of 0, then all of the oxidation numbers, when added up, have to also equal 0. If there's a charge on that compound, so if there's an ion that's present, all of the oxidation numbers have to add up to that charge, positive or negative. You have to take the sign into account. And the oxidation number of a monoatomic ion is then equal to that charge of that ion. So if I have O2 minus, then my oxygen has an oxidation number of 2 minus, because my oxidation numbers have to add up to that whole, my oxidation numbers of my elements have to add up to the overall charge. There's only one element and it has a charge, then my oxidation number of that one element is that charge. For the summing to 0 example, we had HF. We said H had a +1, F had a -1. HF has an overall charge of 0, so +1 and -1 equal out to 0. And we'll look at this one more specifically through our examples. It's just a little bit easier to explain through examples. Our final guideline is to know the elements that nearly always have the same oxidation number. So there are some elements on our periodic table that have only one oxidation number, or most of the time have the same oxidation number. And those elements are in this table. There are some exceptions for some of these, but most of the time they follow these rules. So fluorine will always have an oxidation number of -1. There are no exceptions to that. If you see fluorine, it'll have an oxidation number of -1. A group 1 or 2 metal will always have an oxidation number of +1 or +2, respectively. So group 1 will have an oxidation number of +1, and group 2 will have an oxidation number of +2. There are no exceptions to that rule either. So if you see sodium, you know its oxidation number is +1. If you see magnesium, you know its oxidation number is +2. Okay? So, no exceptions to that. Hydrogen will always have an oxidation number of +1. The only exception to that is if it's with a group 1 or group 2 metal and form a metal hydride. So if we have LiH or CaH2, well then our group 1 and 2 metal oxidation number rule wins out. So this is kind of like a hierarchy. Fluorine is going to be the top one. Then you have group 1 or 2. So when we have LiH, the oxidation number of lithium is +1. The oxidation number of hydrogen can't also be +1 because that would sum to a charge of +2. The charge of LiH is not +2, so that is incorrect. Therefore, if the oxidation number of lithium is +1, the oxidation number of hydrogen must be -1 in order to equal out to its charge of 0. So that's why hydrogen will always have a charge of +1 unless it's with a metal, it makes a metal hydride, so group 1 or 2 metal. Oxygen will always have an oxidation number of -2. The only exceptions to this is if we have any combination with something higher on this list that follows Rule 2 of our assigning oxidation numbers. And this would specifically be for peroxides or KO2, something along those lines. But we will rarely see these examples at this level of general chemistry. You'll probably see these more so in general chemistry 2 when we talk about oxidation reduction reactions in terms of electrochemistry. So for what we're doing here, we will always assume that oxygen has a -2 for its oxidation number. Our final group of elements that have reliable oxidation numbers is going to be group 17, with the exception of fluorine. Fluorine is going to be at the top and always have the oxidation number of -1. So group 1, or group 17, our halogens, are always going to have an oxidation number of -1, unless the exceptions are any combination with something higher on this list. Okay, that follows our rules for assigning oxidation numbers, so we have some examples there. So like ClF, well, fluorine is higher on the list, so it's going to take precedent of having a -1. Chlorine also can't have a -1 because that would equal to -2, and ClF does not have a charge of -2. Okay, so we can't have that. So what our oxidation numbers would look like is fluorine having a -1 and chlorine having a +1 to cancel out and give a neutral charge. Okay, so those are our exceptions to group 17. Everything in group 17 except fluorine. Fluorine will always have -1. You are going to want to memorize these specific oxidation numbers. If you know these oxidation numbers, then you can find the oxidation numbers of any other element. Okay, so we're going to practice that today. So the first one we're going to practice together is assigning the oxidation numbers of each element in the compound KMnO4. So the first thing you want to do is we want to write KMnO4. Now, I like organization, I like tables, if you couldn't tell by my balancing lesson, okay? Your textbook also does a kind of table way of doing oxidation numbers. I personally find it very useful. So we use circles and squares to denote our individual oxidation numbers and our total contribution to the molecule overall. So we start with circles at the top and squares at the bottom. The circles are going to be the individual oxidation numbers, and the squares are going to be the total contribution. Okay? So, the first thing you want to do is start out with the oxidation numbers you know. Well, K is in group 1. We know group 1 will always have an oxidation number of +1. So we know K has +1. So we know its oxidation number is +1. We put it into the circle because that's the individual oxidation number of just one potassium. We don't know manganese. We don't have any rules for manganese, but we do have a rule for oxygen. Oxygen will always have a -2. So that's just for one individual oxygen atom. So we put that in the circle because it's for an individual oxygen. In KMnO4, there are 4 oxygens. So the total contribution of oxygen and its oxidation number to the entire molecule is going to be 2 times 4. So we would get a total contribution of -8. Okay? So potassium, there's only 1, so its total contribution is +1. So now, this is again, like I said, it's similar to Sudoku. We can now fill in the blanks to find the remaining oxidation numbers. We know that this molecule overall has a charge of 0. So the boxes must add up to the charge. So that's step 2. The number in the boxes must sum to 0. KMnO4 is a neutral compound. So if I have -8 and +1, what does the oxidation number of manganese have to be in order to equal out to 0? It would be +7. +1 + 7, that's +8. -8 is 0. Since there's only one manganese, the individual oxidation number of manganese would be +7. Okay, so you now fill in the boxes in the same, kind of in like a reverse order. Again, very similar to a Sudoku. So if we were asked for the individual oxidation numbers for each element, K would have an oxidation number of +1, manganese would have an oxidation number of +7, and oxygen would have an oxidation number of -2. So we're looking at the oxidation numbers of the individual elements, not its overall contribution to the molecule. So we were only looking at the circles. Okay, let's keep practicing. I realize that I have H2SO4 twice, so what I'm going to do is cancel this one and give us a new example. And that new example is going to be C6H12. So we don't need that one. Okay, so I have our circles and our squares all set up for these. I'm going to do the first few and then you'll pause your video and finish the rest. So what we want to do is, to start these problems, put in our oxidation numbers that we know based off of our rules. Well, we know that hydrogen is always going to be a +1 and oxygen is always going to be a -2. So that's what we would put into the circles. The individual hydrogen atom has a +1 and the individual oxygen atom has a -2. Since there are 4 oxygen atoms, the overall contribution would be -8. So we take that subscript and we multiply it by the individual oxidation number. The same would then go for hydrogen. We would take that 2 and multiply it by +1 because the overall contribution of all hydrogen atoms is +2. H2SO4 overall has a charge of 0. So what does the oxidation number for sulfur have to be in order to have an overall charge of 0, given that the contribution of oxygen is -8 and the contribution from hydrogen is +2? That would be +6. 2 + 6 - 8 is equal to 0. Since there's only one sulfur, that +6 is the oxidation number of sulfur. Okay, let's do ClO3 together because this one has a charge, and I said the easiest way to show that rule of assigning oxidation numbers with charges is through practice. So we follow our same rules of determining your oxidation numbers of the elements you know first. So we know oxygen is going to have a -2 charge. Since oxygen lies higher on that chart than chlorine, we can't use our typical -1 chlorine rule. We can't use that, okay, because chlorine would have to be a positive. Okay, we have to have both positive and negative oxidation numbers. So the oxygen rule is higher than the chlorine rule. So we take that value of oxygen first. So we have oxygen being -2. There's 3 of them, so that overall contribution is -6. Now, since this atom, or this molecule, has a charge of -1, this has to equal -1. So the sum of the boxes has to equal 1. So what charge does the chlorine have to have in order to make this have a -1 charge? That should be -1, sorry. -1. What charge does chlorine have to have, or what oxidation number does chlorine have to match that -1 charge? Chlorine would have to have a +5, because +5 minus 6 equals -1. There's only one chlorine, therefore the chlorine oxidation state is +5. A good way to visualize these two examples in comparison of their total contribution and their individual oxidation number is if we draw out the structure. So the structure of H2SO4 looks generally like this. There's some double bonds here. You don't need to know how to draw this, okay? This comes with significantly more practice, but that's the structure of H2SO4. Each of these individual atoms has an oxidation number, and overall the molecule has to equal 0. So we know that hydrogen has a +1 charge, but because there's 2 of them, we have to account for it twice. For oxygen, they each have a -2. So we have to account for all 4 of those individual atoms in the molecule because they all contribute to the overall charge of -0. Therefore, sulfur has to have a charge or an oxidation number of +6, okay, in order for all of these oxidation numbers to cancel out and we get an overall charge of 0. Okay, so when we say total contribution, we have to multiply it by those subscripts to account for the different atoms that are in the molecules. Okay, if there's multiple of those atoms, we have to account for them multiple times because each individual atom has a specific oxidation number, but if there's more of them, it contributes more. Okay, so when we say total contribution, hopefully seeing the structure and why we have to multiply it makes sense. Okay, so what I want you to do now is try these 4 examples. Just remember to change this one in your lecture notepad to C6H12, okay? So remember to change that, but pause your video and try these examples. For our first example, we have HPO3. So we follow our rules. We know hydrogen and we know oxygen. We know hydrogen is +1 and oxygen is -2. There's 3 of them, so we want to multiply those oxygens, so we get -6. Hydrogen, there's only 1, so its total contribution is +1. HPO3 has an overall charge of 0, therefore the total contribution from phosphorus has to be +5. And since there's only 1, its individual oxidation number is also +5. Our next example now changes what our oxidation number is going to be for phosphorus, but we're going to follow the same rules. We know oxygen, -2. We know hydrogen, +1. So there's 3 hydrogens, so its total contribution is now +3. And there's 2 oxygens, so its total contribution is now -4. H3PO2 still has a charge of 0. Therefore, the oxidation state of phosphorus is now +1. +3 + 1 - 4 = 0. So now our oxidation number of phosphorus changes to +1. So those rules that we have for individual atoms, they're there because they have reliable oxidation numbers that are usually unchanging. All of the other elements on the periodic table have various numbers of possible oxidation states or possible oxidation numbers depending on what they're paired up with. So that's why we have to do this. We have to use our rules because we have some elements that have specific oxidation numbers, and we have to use those in order to determine our other ones. So we next have SO3. We only know oxygen's rule, that's -2. Its total contribution is -6. Overall, we have a charge of 0, so the total contribution from sulfur should be plus 6. There's only one sulfur, so we have to have an oxidation state of plus 6. In our last example, this is where we get a little bit trickier, okay? For this one, we still follow our rules. Hydrogen is still going to have an oxidation number of plus 1. Yes, it's in the second spot, so it's going to look a little funny, but that's okay. So hydrogen has a plus 1 charge, okay? It's not with a group 1 or 2 metal, so it does not have its exception. There's 12 of them, so its total contribution is plus 12. Overall, C6H12 has a charge of 0, okay? So the total contribution from carbon in total is going to be minus 12. Because there are 6 carbons, we want to find the oxidation state of each carbon individually. Well, if the carbon contribution overall is minus 12 and there are 6 of them, how do we distribute that minus 12 charge over all 6 of them? Well, we take 12 and we divide it by 6. So we get a total contribution of minus 2. So the individual oxidation state of each carbon is minus 2. There are 6 of them, so overall it contributes a minus 12. So we're working backwards here. When we went from 12 to 1, okay, we had to multiply, and we went from square to circle to square. Now if we want to go from square to circle, we have to divide. So we can write that circle to square, multiply by subscript, and square to circle, divide by subscript. Okay, so that one was a little bit tricky. Okay, let's do some more. For these ones, we want to determine the oxidation number for the underlined atoms in the following molecules and ions. So, even though we're only going to identify the underlined atoms, which you may find similar problems in your homework, we still need to find the oxidation numbers of all atoms in the molecule, okay, in order to properly account for their oxidation numbers in contribution to their charge. So for these ones, we're really just finding the oxidation numbers for all of the atoms. So pause your video and try these problems fully independent. Okay, go through each molecule, identify the oxidation numbers of the ones that you know following those rules. The ones that you don't know, we already did KMNO4, so we already have that one done. So see if you can remember how to do that one. Account for your charges on some of these appropriately. Okay, try them independently. I did not give you any circles and squares, but feel free to draw them on your own paper. I'm going to take a second and draw these in for myself, and then we'll come back and practice them together. For our first example, IF7, we're going to follow our fluorine rule. Fluorine will always have an oxidation number of -1. There are 7 of them, so its overall contribution is -7. Since this has a charge overall of 0, iodine must have an oxidation contribution of +7. Therefore, because there's only one iodine, its individual oxidation number is +7. So the oxidation number of iodine is +7. We always want to look at our circles for these types of problems when it says to determine the oxidation number of the individual atom, okay, because we're not looking at its total contribution to the molecule overall. We want to look at its individual oxidation number. Okay, KMNO4 was our first example that we did, where we said we have -2 for oxygen, +1 for potassium. So we have +1 contribution from potassium and -8 contribution for oxygen. Overall, this needs to equal 0, so manganese is +7. So the manganese oxidation state is +7. K2Cr2O7. This one's similar to our last one. We know K is +1. We know oxygen is -2. There's 7 oxygens, so that's a total contribution of -14. We have K2, which is a total contribution of 2 from the potassium. Our overall charge is 0, so the overall contribution from chromium has to be +12. When we're going from square to circle, if we have a subscript, we have to divide by that subscript. So we're going to divide +12 by 2 and we get +6. So the the individual oxidation number for chromium is +6 because its overall contribution is +12 and there's 2 chromiums. So we have to distribute that +12 amongst those 2 chromiums. Okay, I'm going to snake around now. I guess I'll go in a serpentine kind of shape. We'll get rid of that little line there so it doesn't confuse us. Antimony and fluorine. So fluorine we know. F is always going to be -1. And there are 6 of them, so its total contribution is -6. This does have a charge, so we want this to equal -1. So antimony's total contribution must be +5. +5 minus 6 is equal to -1. There's only one antimony, so it has to have an oxidation number of +5. Okay, tungsten and oxygen. Well, we know oxygen, -2. There's 4 of them, so -8 total. It has a charge of 2-, so we have to equal 2-. So tungsten must have a contribution of +6, and since there's only one, that is its oxidation number. Our next example is the carbonate ion, CO3 2-. We know oxygen is always going to be -2. There's 3 of them for -6. This has to equal -2. So we need carbon to be +4. There's only one carbon, so its oxidation number is +4. We next have platinum and chlorine, and we have 2 examples of those, where the only thing we change is the number of chlorine. Our charge is the same, but our chlorines are different. So platinum and chlorine, we're going to follow our chlorine rule, so group 17 rule, which says that it is -1. Okay, the only time it's not -1 is if it's with anything, a hydrogen, an oxygen, a group 1 or 2, or fluorine. Okay, so chlorine each has -1. Let's do our first one here. There's 4 of them, so that's -4. This has a charge of 2-, so platinum must have a total contribution of +2, meaning its individual oxidation number is +2 since there's only one. Now let's see how the platinum oxidation number changes when we add 2 extra chlorines on there. So the chlorine contribution in our second example is now -6. We still need this to equal out to 2- or -2. Therefore, the platinum oxidation number must increase to +4 to account for that. So we'd have to balance out those chlorines with a little bit higher oxidation state on the platinum. There's still only one platinum, so +4 is its oxidation number. Okay, and our last example, magnesium and nitrogen. Well, we don't know any rules for nitrogen, but we do know a rule for magnesium. It's in group 2. So if it's in group 2, it has a +2 oxidation state. Since there's 3 of them, its total contribution is plus 6. Overall, this has a charge of 0, meaning that the contribution from nitrogen must also be minus 6. There's 2 nitrogens in there, so we have to distribute that minus 6 amongst them. So its oxidation number is minus 3. So when we go from square to circle, we divide by our subscript. Okay, those are our oxidation numbers for all of those examples. We've done a lot of examples. If you like Sudoku, you'll love doing this. I love doing Sudoku, and I love doing oxidation numbers. So, because it's just kind of just figuring it out and multiplying, dividing, and everything like that. So, real fun.